Okay, homework 2, part 3. Our questions are using the results from B2 derive an expression for the overall thermal resistance of a pipe of radius R1 wrapped with insulation to radius of R2. And then determine expression for the first and second derivative and explain the practical consequences. So let me just kind of draw what we have here, what we're doing. So this is going to be a really rough sketch, but it will work. So our R1 is going to be at this value. So I'll mark it in orange and put R1, and then our R2 I'll do in green, and it's going to be out here. So we're going to use this equation from what we just did in part B, and we're going to use that equation from part B, and we'll get right into it, starting with simplifying stuff. So we'll get our R total will be equal to natural log of R2 R1 over our area, well, K, and then our area 2 pi L. And then we have to add our second part over here, which is also our area, so HA, and then 2 pi RL again. Well, R2, that is. So now what we kind of need to do is what it says up here, do the first and second derivative. So that was kind of part A. We have one here. So part 2, we're going to do our first and second derivative of these values. And we need to find our critical point and also our critical insulation, so our optimal insulation values. So let's start with our first derivative, which will give us our R2, our critical point. So we're gonna get, let's do a derivative of our R total, or derivative of R, and that's gonna be equal to 0. So we can further go into that. Sorry if there's any commotion, it's really windy. So we're gonna have negative 1 over H2R, or sorry, HAR squared times 2 pi L, and then that's gonna be plus derivative. So R1 over R2 times 1 over R1 over just the same value, 2 pi L. So we can already see things are going to cancel. So our R1s will cancel here, and our 2 pi L will cancel. Correct? Yeah. Okay, so now we can just simplify that expression to be 1 over HAR, 1 over HAR squared plus 1 over K R2. Okay. Looks good. Then we just need to solve for R2. So let me write that. Solve for R2. So still recording, good. Okay, so R2 is going to be equal to K over HA is equal to 0. Yep, okay, cool. Awesome, so now what we have to do is we have to do our second derivative to find the, that was finding our critical point, so we have to do our second derivative to find our insulation values and show kind of what we have to explain in part 3. So we're still in part 2. So do the second derivative now. and that will be equal to, let me go up, equal to 2 HAR2 squared minus 1 over KR2 squared. Okay, looks good. And then now all we have to do is just plug in. We're going to use this R2 in these values, so just do that quick. Okay, cool. Awesome. So now we just have to simplify our values. Cool. So we'll have 2 over HA cubed, or sorry, squared, over K minus HA squared over K cubed. So what we can kind of see here is, since we have same denominator, that's not going to matter, and since we have both of our HA values squared, that will always afford a positive value. So that also kind of demonstrates that K over HA will always be a minimum. Because of the reciprocal. So now kind of jumping into part C, I'm just gonna kind of draw this here. So we'll have a minimum and then we'll start to come back up. Hopefully that was okay, cool. So at this will be our R1 at these origin, and then here will be our R2 at the minimum, and K over HA is just our line. That's demonstrates our line. So the reason that there is a minimum at this outside insulation, I guess I should go up here. At this outside insulation, the reason that this is a minimum out here on this line, I'll mark it in red, is because there's more convection happening rather than conduction via our resistances. So, yep. That kind of explains our 3 questions. We did A up here, we did 2, and C, we explained our practical consequences. And we explained why there is a minimum value for R2. So, looks good. On to part 4.